Hello everyone, today we'll present our project Personalized Video Recommendation System to you. Our project aims to develop advanced machine learning-based system for personalized video recommendations. In order to achieve that, we learned the evolution of the recommendation methods. We've leveraged the Movie Lens 1M dataset, which includes 1 million ratings from 6,000 users across 4,000 movies for our code implementation. In today's digital age, the rapid growth of online streaming media platforms has led to a significant content overload. This often makes it challenging for users to discover videos that truly capture their interest, negatively impacting user engagement. And traditional recommendation systems falling to recognize individual user preferences and needs. For our project, we will focus on analyzing user viewing histories and preferences to create recommendations that are not only relevant but also deeply personalized, enhancing user satisfaction and retention. In our approach, we utilize active sampling as a key data processing method for the neural collaborative filtering model. Since the NCF model primarily deals with implicit feedback, which includes only positive interactions, negative sampling is crucial. It helps generate the necessary negative interactions to balance the dataset, ensuring robust model training and evaluation. Here's how we implement it. We start by extracting all positive interactions from the dataset. Then, for each user, we randomly select a set number of items they have not interacted with and creating our negative samples. Finally, we combine this with the positive interactions, labeling positive as 1 and negatives as 0 to form our training dataset. This method is essential for measuring the model's performance accurately, using metrics like the hit ratio. For our method one, we utilize neural collaborative filtering, which is NCF, for our video recommendation system as it blends deep learning with traditional collaborative filtering. This integration enhances matrix factorization by capturing complex user item interactions dynamically, suitable for varied data characteristics. Collaborative filtering alone focusing on similarities in user rating and adapts without needing specific content details, making our recommendations adaptable and personalized. The NCF model starts as an input layer, which user and item IDs are transformed into embedding vectors to capture latent features. In the embedding layer, these IDs are converted into dense vectors. The hidden layer, consisting of GMF and MLP components, models both linear and nonlinear interactions between users and items. Finally, the output layer synthesizes interactions to compute the final recommendation scores, optimized through a loss function that balance observed and negative interactions for accurate relevant scoring. In our model, we integrate GMF, which performs element-wise multiplication of user and item latent vectors, with a MLP that captures complex nonlinear interactions through multiple neural network layers. This combination forms our neural matrix factorization, which enhances recommendation accuracy by combining the simplicity of the matrix factorization with the depth of neural networks. We implement new MF in two ways. First, by sharing embedding layers between GMF and MLP, and second, by fusing their outputs as the last hidden layers. The dual approach allows us to model user-movie interactions with both linear and nonlinear dynamics, optimizing our system for varied user preferences and behaviors.
We address the cold start problem in NCF model for recommendation systems where new users lack historical interaction data. To solve this, we turn to unsupervised learning methods, PCA and K-means clustering. PCA, or Principal Component Analysis, was used to reduce the high dimensionality of the movie genre features. Our dataset includes 20 movie genres, but each movie typically has only 2 or 3 associated tags, which makes clustering difficult. PCA transforms this data into a low-dimensional space, retaining the most critical information while improving clustering performance. After PCA, we applied the K-means clustering algorithm to group movies with similar content. K-means minimize intra-cluster variance and ensures well-defined clusters. Now, moving beyond clustering, we revisited our neural collaborative filtering NCF model to enhance its performance. we incorporated an attention mechanism and hierarchical fusion layers. The attention mechanism adjusts the weight assigned to different features during learning, allowing the model to focus on critical components. For instance, it helps capture linear relationships through generalized matrix factorization and nonlinear patterns through multi-layer perceptrons. Hierarchical fusion refines the combination of features using multiple fully connected layers with dropout regularization, improving the model's ability to learn complex relationships. This advanced architecture significantly boosts recommendation accuracy. Our results demonstrate the effectiveness of this method. For the improved NCF model, key matrices like hit ratio and normalized discounted cumulative gain showed consistent improvements. For PCA and K-means clustering, we evaluated the quality of clusters using matrices such as the CLO8 score and CH index, both indicating strong clustering performance. Here are the results for the NCF model. These matrices demonstrate the model's ability to accurately include relevant items in recommendations and rank them effectively. Specifically, we observed faster convergence after incorporating a dropout layer for regularization, improving the hit ratio to around 0.80 and the NDCG to 0.54. For PCA and K-means clustering results, based on the elbow method, we determined that 4 clusters provided the best results. For each cluster, we selected the 2 highest rated movies and used them as recommendation for new users. And finally, we got the 8 movies recommendation. The advanced NCF model demonstrated consistent improvements with both hit ratio and NDCG matrices showing upward trends across iterations. This indicated that the model successfully captures deeper user-movie relationships, resulting in more accurate and meaningful recommendations. To conclude, our approach combines unsupervised and supervised learning to address challenges in recommendation systems. PCA and K-means clustering handle the cold start problem effectively, while the advanced NCF model provides highly personalized recommendations. For future work, we plan to test these methods on larger, more diverse datasets to validate their scalability and robustness. Additionally, we aim to explore further architectural optimizations to improve the performance and generalizability of the recommendation system. Here is our reference list. Thanks for the listening.